What is going on, everybody? Welcome back to my YouTube channel, Richard on Data. And if this is your first time here, my name is Richard, and this is the channel where we talk about all things data, data science, statistics, and programming. So subscribe for all kinds of content just like this if you haven't already, and hit the notification bell so YouTube notifies you whenever I upload a video. So this is another video in my R tutorial series. The last video in this series was all about creating linear models. So you create some model object using an LM or a GLM function. But okay, what exactly is the structure of that object that you created? And then how do you extract useful properties from it? Then I also covered how you actually get these things into more of a tidy format using the Broom package. Now, one thing I didn't really cover all that much in that tutorial was the interpretation side of things. So that's what we're going to talk about today. So we're going to talk about the high-level idea, why you would want to use linear regression or logistic regression methods in the first place, and then once you've spun up these functions using LM or GLM, okay, how do you actually interpret these things? So before we get started, hit the like button for the YouTube algorithm. This script will be available on my GitHub repo. That's going to be linked in the description of the video. And now you can watch these tutorials in either order. So if you haven't watched R tutorial 10, I do recommend watching that one first, but it's not absolutely necessary. You can watch this one first. But I'm going to be working with, just like I did in that tutorial, the MT cars and the credit card data sets for my linear and logistic regression examples. And so the details of how I created these and why I did a few things that I did beforehand are going to be available in R tutorial 10. So without further ado, let's get started. All right, so let's start with the high-level idea behind regression. What exactly is going on, and why would you want to do this in the first place? So regression methods are completely analogous to that slope-intercept equation that you probably remember from back in high school. That is, y equals mx plus b. And what that equation basically means is you're explaining the rise or the change in some variable y in terms of the run or the change in some variable x. Meanwhile, you've got m, that's your slope term, and b, that's your intercept term. So that's basically exactly what we're doing when we do any kind of regression method. So we're using these methods to fit a linear model that explains the variation in a response variable, sometimes called the dependent variable, linearly in terms of other variables. These are typically known as the independent or explanatory variables. I just call them predictors. And so you create a linear model which is going to output some fitted values y hat. You have the actual values, that is the y, and the idea is we're using a least squares solution. Now what that means is if you take that difference, the difference between the actual and the fitted values, we want the sum of all of those square differences to be as small as possible. That's the least squares solution. And now I'm going to give you the matrix interpretation of this. Now, if you don't know linear algebra, this part may go over your head, but at least just be aware of the notation. So the least squares equation for the estimate of the slope parameters, that is beta hat, equals x transpose x, all of that inverse, times x transpose times y. So again, just be familiar with the notation here. Beta is the vector of true slope parameters for the whole population. Beta hat is a vector containing the estimates of the true slope parameters. That's the thing that we're trying to create here. X is your matrix of predictors, and y is the response vector. So most important thing here is the predictors are typically going to be denoted by x is the matrix. Then x1, x2, x3 are the individual predictors, and then y is your response vector. Now, I really want to emphasize one of the key assumptions here. So take your response y, and then just pick any predictor, call that x1. So the assumption is, in the population at large, there is a true slope parameter, let's call that beta 1 here, that explains linearly the variation in y in terms of a 1 unit change in x1. That's the assumption. Now, it's just like any other parameter. We can't truly know that slope parameter, but through linear regression, we can come up with an estimate for that slope parameter. That's our estimate, beta hat 1. So that's a little bit different if you have a Bayesian interpretation of statistics, but the difference between the frequentist interpretation and Bayesian interpretation is completely the subject, not even for one more tutorial, but for a whole other series. But for how most people approach this, which is the frequentist interpretation, that's the true assumption on the back end. And so you're going to get regression output, which is going to return your estimates of these slope parameters. That is, let's just call that a vector beta hat that's got individual estimates, beta hat 1, beta hat 2, so on and so forth. Naturally, any estimate or any statistic is going to carry with it a corresponding standard error. And then putting those things together, you can create a test statistic and a p-value. So the test statistic for linear regression is a T-statistic. For logistic regression, it's a Z-statistic. And you're testing a hypothesis of that true corresponding slope parameter being different than 0. So think about this. If the true slope parameter is 0, that means as x changes, y is not going to change. So there's no true relationship, at least in a linear sense, between these two variables. Now, if that null hypothesis is false, that is, that true slope parameter is not equal to 0, then that means as x changes, y is going to change. So that tells you there is actually some kind of linear relationship between these variables, and that's the hypothesis that we test. We'll see some examples when we look at real output here. Now, I really do want to emphasize there are two distinct goals that you can get at with regression methods, and those are prediction and inference. Now, I have a whole video delineating the difference between these two, so check that out if you haven't already. But at a high level, suppose you created that regression equation and then you just get new data, okay? And in that new data, let's say you have values for all of your predictors, but you're missing that response. Well, you already have a full linear equation that you can just plug the predictors into, and then you're going to get predictions for that response. So you can use this completely for predicting that response. It's typically going to underperform things like traditional machine learning methods. But all the same, I mean, it can be used, and you have the benefit of just interpretability and understanding exactly where your prediction is coming from. Now, again, completely distinct from that is the fact that regression methods can be used for inference, and I've already explained at a high level exactly what's going on, but the idea is these estimates of slope parameters are used to estimate how much the response variable will change per 1 unit increase in each continuous explanatory variable or per change in levels in the categorical variables. And so we'll see examples of that once we look at the actual output. So I'm going to run the exact same regression that I did in our tutorial number 10. And again, you can go over to that one for the details. But I'm going to go through and interpret for you every piece of this output. So we start out with the model call. All that's just the function that's getting run in R. Then the next thing that we have are the residuals. Now the residuals are just the difference between the observed values, that is the actual y's, and the predicted values, or the fitted values, that is the y hat. And now this is a very similar idea to the fact that the slope estimates that we calculate, they are estimating true parameters, true slope parameters. And these residuals are just statistics which estimate true population errors. So just keep that in mind. Now, there's an assumption on the back end with regression that these true population errors are normally distributed with a mean equal to 0 and constant standard deviation. That is, there's no real pattern to the true population errors. And you can do things like just graph out your residuals to test how valid that assumption is. Moving on, the real meat and potatoes of the regression output is this coefficient table here. And so what we've got here are the estimates of the slope parameters. Every statistic or estimate is going to carry with it a standard error. So those values are reported here as well. And again, we've got t-values and corresponding p-values. And so again, for the most part here, what we've got for continuous variables is the estimate and how much we expect y to change for a 1 unit change in that corresponding x variable. Now, there are a couple differences here, and so I want to draw attention here to some specific special cases. So let's take this disp variable here. So I did a transformation when I created this linear regression equation here. I'm modeling the response variable MPG in terms of the square root of this DISP variable. Now, it's still pretty straightforward. For a 1 unit change, or 1 unit increase specifically, in the square root of the DISP variable, I expect MPG to change by negative 0.0732, okay? Not that much to it. Now, another thing I do want to draw attention to is categorical variables or factor variables. And an example of that is the CYL variable here. So it's important to understand with these factors, when you look at these slope estimates here, these are with respect to a baseline. So this CYL variable, it takes on values 4, 6, or 8. Now, your baseline here is 4. So let's just assume here that we have a car with CYL equals 8. Now, if we hold all other variables constant, we expect that car with CYL equals 8 to have MPG of 0.09762 greater than the car with the baseline CYL equals 4. Okay, so again, most important thing to understand with these factor variables is these estimates are just compared to some baseline. Now, the last thing to draw your attention to is this interaction term here. So generally, when we add terms to this linear regression equation, we are assuming that the cumulative effect of all these things is additive, but we change that assumption around when we add interaction terms. So there's an interaction term here between the variables HP and weight, that is WT. So let's just assume we have 1 unit increases in HP and WT. Okay, we would then expect MPG to change by negative 0.10267 plus, that is negative 8.25722, and then plus 0.02657. So again, if these things are both increasing, the net effect of that on our response variable is not necessarily additive. Now let's just quickly touch on these t-statistics here and these p-values. So you'll notice that next to the intercept term, as well as HP, WT, and this interaction term, that these p-values are starred. This means they're significant at a particular level of significance. For this example, let's just say 0.05. So remember, we are testing against a null hypothesis that these individual slope parameters are equal to 0. Since these p-values are lower than 0.05 in this case, we are rejecting these null hypotheses. So we can conclude these true slope parameters are different than 0, meaning in the population at large, there is a statistically significant effect that these variables have on our response variable MPG. Now, statistically significant does not necessarily mean the same thing as practically significant. That's a whole other can of worms there. But that's the interpretation behind these t-statistics and the corresponding p-values. Now let's wrap up with these last few terms at the bottom here. So starting with residual standard error, this is a super important quantity. Now, this is an estimate of the standard deviation of the true population errors, but think of it analogously as how wrong the model is on average. So it's also in the case of linear regression, it's equal to the quantity root mean squared error. And when your goal is prediction, This is a really good goalpost for the quality of your model. Now, the lower this thing is, obviously the better, because that's telling you your model is less wrong on average the lower this thing gets. Moving on, we've got multiple r squared. This is a quantity known as the coefficient of determination. And this is the proportion of the variation in the response variable that can be explained by this linear regression model that we're using. So, very important quantity. We're basically saying 89.3% of the variation in this MPG variable is explained by this model that we've built. But there is one very important drawback to this quantity, which is as we add more predictors, this thing is either going to stay the same or it's going to keep going up and up and up. Having said that, adding more predictors is not necessarily a good thing because it means you're just going to create a regression model that overfits. So to correct for this problem, you've also got this quantity called adjusted r squared. So this corrects for this issue, and the formula for it can be seen here. Adjusted r squared equals 1 minus, and in parentheses 1 minus r squared times n minus 1 all over n minus p minus 1, where n is the total sample size and p is the number of predictors. And basically what's going on here is this quantity penalizes additional predictors. So we're balancing here, explaining all the variation in our y variable with how much are we overfitting, how complicated are we making this model. Lastly, we've got this F statistic. And now, interestingly, suppose we had only one predictor in the model. Actually, that F statistic would just be equal to the square of that corresponding T statistic. But generally speaking, this isn't really something you have to worry about that much. You are testing whether or not the linear regression model fits the data better than a model with no predictors. Notice that we have an extremely low p-value here, as we expect. So again, a high F statistic and a corresponding low p-value would just indicate the model does fit the data better than a model with no predictors. Now, this is, again, not something that you have to worry about all that much. That covers it for linear regression, and now we're going to move on to logistic regression. So the key difference between the two is that with linear regression, we had a continuous response variable. Now with logistic regression, we have a categorical response variable. Now, the thing with logistic regression, when most people talk about it, they're specifically referring to binomial logistic regression. That is the case where your response variable is a categorical variable with two levels. Typically, we're going to refer to those as success and failure, or 1 and 0, where you've got a probability of success that's equal to p, and then your corresponding probability of failure is equal to 1 minus p. Now, a term, just to understand the theory here at a high level, to be familiar with, is odds. Now, that's a ratio of the relative probabilities. That is, p divided by 1 minus p. So for instance, suppose I'm rolling a 6-sided die. The probability that I'm going to land on a 6 is 1 over 6. But these odds here are actually 1 over 6 divided by 5 over 6. That is 1 over 5. So another key assumption here, just to be familiar with, is the fact that with linear regression, your continuous variable could go all the way from negative infinity to infinity. So that's obviously not the case with probabilities or with odds. You're going to go from 0 to 1. However, what goes on with logistic regression is you get around that issue by taking a transformation known as the log odds of the probability. So the log odds is just the natural log of p divided by 1 minus p. And this quantity here, the log odds, is sometimes known as the logit. And so our logistic regression equation is just the logit of p equals same thing as it did before. We've got all of our x variables, and we've got corresponding slope estimates to them. So logistic regression is significantly more technically and mathematically complex than linear regression, but the high-level idea behind it, all the same, most stakeholders are going to understand. Now, one concept that I want to introduce here at least a high level, and again, this may go over your head a little bit if you don't know statistics too much already, but just be familiar with the terminology at a very high level, is the deviance. So the deviance is defined as the degree to which the likelihood, that's again a statistical concept, of the saturated model exceeds the likelihood of the model that we're creating here, where the saturated model is just a model with as many parameters as you have observations. That is a perfect fit type of model. So just at a very high level, just understand the lower the deviance that we have, the better, the higher quality of fit that we have. So again, I'm going to create the exact same logistic regression model that I did in our tutorial number 10. And now let's look at the output here. First thing you've got under the model call is the Deviance Residuals. And these are completely analogous to the residuals that you saw from linear regression. Every deviance residual corresponds to an observation and how much it contributed to the total deviance. That is, the variation from the perfect fit. That's all you got to understand with that. We've got this coefficient table here, and again, it's got a very similar sort of interpretation to the linear regression coefficient table. We've got a linear equation going on the back end. So let's just take, for example, the income variable here. Notice that there's a slope estimate here of 0.34592. So for a 1 unit increase in the income variable, we expect the log odds of the success of a response variable here, that is, a credit card being issued. We expect the log odds of that to go up by 0.34592. Now, you can do a conversion there to see how the probability changes from unit to unit, but at its highest level, just understand that if you have a positive coefficient here, then as income increases, we do expect the probability of our response variable, the credit card being issued, to go up as well. Then lastly, we have some more metrics indicating the quality of the model fit. So starting with this null deviance, that's generally not something you're going to have to worry about. That is the deviance in the situation where you have a model containing only the intercept. So you would expect the model with only an intercept term is not going to fit very well. As a result, you're going to have a very high deviance. Then meanwhile, you've got the residual deviance, which indicates the goodness of fit for the model that we created. Now, we expect this to be much lower if we have a good model than the null deviance. So in this case, that appears to be the case. Now, then you've got AIC. So AIC is also a quantity that you can get from linear regression. This stands for the Akaike information criterion, and this is just another metric that describes the quality of the model fit. And it's a pretty nice quantity because this is another quantity that increases as parameters are added, and having a higher AIC is a bad thing. So lower the AIC, the better of a model fit that you have. You're also provided the number of Fisher scoring iterations. All this is the number of iterations that it took for the model to converge. For most people, that's not going to be particularly interesting. So that just about covers it for linear and logistic regression. Just to provide you a high-level introduction to the output that you get from R, and then how do you interpret all of this. Now, this is an incredibly broad field. You can get into things like model selection, weighting the models, other types of generalized linear models. So there's a ton of depth to this field, but it all starts with having a clear understanding of these things and being able to explain it to stakeholders. So just start there, master it, and then move from there. So I'll leave you all with that. Thanks for watching this video. If you enjoyed it, hit the like button, consider sharing, and then I'll see you all in the not so distant future. Until then, Richard on Data.